Hi everybody, today we're going to start talking about our last study of motion, and that is projectile motion. So our objectives for this lesson are to be able to define a projectile, to recognize that the horizontal and vertical components of a projectile in motion are independent of each other, and to solve problems involving objects in projectile motion. So first, let's define a projectile. A projectile is an object that's acted upon only by the force of gravity as it moves through the air. That should sound familiar. It should sound very much like free fall. And that is because an object in projectile motion moves in a very similar manner to free fall motion. Just like free fall, we neglect air resistance. You may think about objects as they move through the air that we might think about as projectiles, things like tennis balls, baseballs, footballs, and you may say, well, they all move through the air differently. And that is true in the real world. That's because the shape, the size, the mass, the texture of the ball all interact with the air around it to move differently. But if we neglect air resistance, it turns out that all things look the same and all things will travel the same. So typically, projectiles that we're going to look at are objects that are launched horizontally from an elevated height, something like here, similar to what we started with free fall, or thrown upwards but at an angle. So where we started talking about free fall and we said directly up and directly back down again, essentially an angle of 90 degrees, we're going to start talking about objects that are thrown upwards but at an angle somewhat less than 90 degrees. Let's compare free fall and projectile motion. So we started talking about free fall. We said an object was dropped from rest from an elevated height. So we knew that its initial velocity in that vertical direction that it was traveling was 0. We knew that gravity would accelerate it as it moved down towards the bottom of its motion. And we knew that gravity sped it up at that rate of 9.8 meters per second squared. And that each subsequent second, the object was traveling more and more distance because it was traveling faster and faster due to gravity's acceleration. Well, when we start looking at objects that are similar to that, but are launched horizontally from an elevated height, we still have those same things going on. We still can say that vertically, the motion is 0 when it is first launched. Gravity still accelerates it and speeds it up as it travels towards the ground. The only thing here is because it was launched horizontally, there was a horizontal or x direction component to its velocity that moves it in the horizontal direction as the object actually falls to the ground. When we talk about an object being thrown vertically upward in free fall, we said that the object would go straight up, gravity would slow it down until it reached its peak. At that point, the acceleration due to gravity would turn it around and then speed it up back down. The same is true here as if we launch or throw an object into the air at an angle that is not 90 degrees, not straight up. It still goes and travels up to a peak, and then gravity speeds it up as it comes back down again. But during that entire period of motion, there was a horizontal piece of the initial velocity that moves the object in the horizontal direction as it travels up and comes back down again. So objects that are in projectile motion follow a set of rules. And if you can remember them, they sort of help understand how we can solve problems when objects are in projectile motion. First of all, projectiles travel in a parabolic shape. A parabolic trajectory. That's the path it follows as it moves through the air due to the influence of gravity. So you are used to things going through the air and watching them. They travel in that nice arc, and that's that parabola. Even if you think of the objects that are launched horizontally from an elevated height, that's essentially starting somewhere around here, and the object still drops with that nice curved or arc shape. It just happens to be the second half of this type of arc. The horizontal motion of a projectile is independent of its vertical motion. And we want to be able to say that because it makes our problems easier to solve, but we can also say it because when we start to talk about velocity, remember velocity is a vector. And back when we talked about displacement and distance, and we did some of our breaking of our displacement into components, we can do the same thing with velocity. And we're going to use that same type of vector math and the trig functions that we used before to be able to determine how an object moves horizontally and how an object moves vertically as it travels through its path of projectile motion. Here's a very important part. Only gravity is acting upon the projectile, so as a result, there is no acceleration in the horizontal direction. Let me repeat that. Only gravity is acting upon the projectile. Gravity goes up and down. Just like in free fall, gravity goes up and down. Horizontal goes left to right. So as a result, there's no acceleration on the object in the horizontal direction. Right? As if it's traveling through the air, and you might think about air resistance is affecting it, and it sure is in the real world, but because we're neglecting air resistance, that takes it out of the problem. So what that makes it very easy to understand is that the horizontal velocity then of the projectiles is constant. It never changes during the entire time the projectile is in the air, because there's no acceleration in that direction in order to change its motion. There is a vertical acceleration caused by gravity, just like free fall. The acceleration is equal to g, which is 9.8 meters per second squared. So when we solve these problems, a lot of what we learn to do in free fall is going to be exactly what we apply when we're talking about projectile motion. The most important part you have to be able to remember about objects in projectile motion, though, is about the time. Time is our link. If the horizontal and vertical directions are completely independent of each other, how can we maybe use information from one direction to solve a problem in the other direction? And that has to do with time. The time traveled in the horizontal direction equals the time traveled in the vertical direction, which is the total time the projectile is in the air. Regardless of how you look at an object as it moves through the air, which plane you are looking at it. If you're looking at it from above, you're just going to see an object move horizontally. And as a result, that amount of time is how much time it takes to move horizontally from one point to another. If you're looking, say, front on, meaning that you're looking behind the quarterback as he throws the football, you would really just see the ball go up in the air and come back down again, but still the same amount of time in the air. And finally, if you looked at the motion directly from in front of it and observed both the vertical and the horizontal components, it's still in the air for the same amount of time. So time is our very important link in projectile motion. There are two types of problems that we're going to look at in projectile motion. The first one is where the object is launched horizontally with an initial horizontal velocity only from some type of elevated position. In that case, the object still travels in that parabolic path. It's just sort of half of a parabola. The initial velocity in the vertical direction is 0, so it acts as if the object were dropped in the vertical direction. But there is a horizontal component to it, so as it drops, it moves in the horizontal direction. So we do have some information about how it moves horizontally. The second type we're going to look at is when a projectile is launched at that angle to the horizontal and rises up to a peak and comes back down again. Just like with free fall, we're going to use a lot of the symmetry of the problem and a lot of the information that we know about what's happening in this problem. So what we're going to be able to say is, in this scenario, initially there is some velocity in both the horizontal direction that moves the projectile in the horizontal direction. There's some velocity in the vertical direction that moves the projectile in the vertical direction or up into the air. We're going to use those trig components like we did with displacement, but we want to be able to realize that a lot of what we've learned in free fall still applies. There is a peak here that has to do with the velocity at that peak. Well, the velocity in the vertical direction, just like at free fall, becomes 0 at that peak. And the acceleration due to gravity is just turning it around to come back down again. We can say things about the velocity that it is launched with is equal to the velocity, but in a different direction, as it reaches the same place where it was launched from. So a lot of that symmetry still helps us out in these types of problems too. So when we're solving these problems, we use the same equations that we've learned before. We use them in one dimension horizontal motion. We use it in one dimension vertical motion or free fall. They don't change. But what we're going to probably do is add another subscript or a way of organizing our information to be able to know what direction that we're talking about at the time we're solving the problem. Because we can't mix and match. We have to be able to say what we're putting into this problem has to do with just the horizontal direction or just the vertical direction. So if we look at just the horizontal direction, because there's no acceleration, every term that has an a in it is 0, so it all drops out. And we end up with our nice constant velocity or constant motion equation of velocity equals distance over time. Or initial velocity equals final velocity. Or essentially the velocity is the same the entire period of motion in the horizontal direction. In the vertical direction, we still use those same types of equations, and again, our acceleration due to gravity is known. It is still 9.8 meters per second squared. If we take it in the negative direction, it slows us down, but all the information that we've already learned from free fall is exactly what we can apply here. So when we look at these, we want to realize that the two components are independent of each other. When we use equations, we have to make sure that we're solving for one direction or another direction. We can't mix and match. So we want to make sure that the equations aren't any different, but we really need to be able to know where we're getting our information from as we plug in that information into our equations. So here's going to be our problem-solving strategy. First of all, we're going to divide the projectile motion into vertical and horizontal motion, sort of like sub-problems, in order to be able to solve information about each direction independently. Remember, we'll solve the vertical motion with the same approach as we did free fall, because the only thing that's affecting the motion in the vertical direction is gravity and the acceleration due to gravity. The horizontal motion is a piece of cake because it's all constant velocity. There's no acceleration in the horizontal direction, so as a result, nothing ever changes. Then what we're going to do is, if we need to maybe get some information that we need to borrow from one direction and bring it into the other, that guy's going to be our time, because our motion in either direction is linked by the time variable. The length of time the object is in the air depends only on gravity, because it's just like throwing something up and having it come back down again. The only thing that's affecting its motion is gravity, but we have to remember that that length of time is the same regardless of which direction we're looking. So what happens with projectile motion problems is it becomes an issue of bookkeeping. It really helps to keep your data organized, and we'll talk about some tricks in class or ways to make sure that you are doing that so that you're not taking information from one direction and placing it in another, because that's where things can screw you up. So you want to remember that you keep your data organized, you solve each problem independently, meaning each direction of each problem independently, and remember that the only variable that is the same for each direction is time.